With 5.2, so we got up to this part here. I was talking about horizontal asymptotes. So horizontal asymptotes and oblique asymptotes are connected because you have to kind of do the same comparison of the degree. So when we look at the degrees, we're looking at the degree here. If the degree is the same on the top and the bottom, so I'll use pink here. So this is degree 1 and degree 1. So both of those are degree 1. If they are the same degree, so same degree, if they're the same degree on the top and the bottom, we just look at the coefficients, right? So the coefficients, right, and I couldn't spell coefficients, it's 2 to 1. So that is why it plateaus to be 2. So remember, what we're looking with a horizontal asymptote is we are looking at what's happening at the end part of the graph. So it's like you're taking, and I always think of this as kind of an experiment. So if we have fish in a pond, okay, it might grow bigger, it might go smaller, and then it's going to plateau to be at 2. So that's what a horizontal asymptote is. It's at the end of the graph. There might be things happening. Oh, there's an explosion, then they all got sick, but then they plateaued. So the horizontal asymptote is at the end, either end of the graph. So it could be negatives if there was a negative scenario, or the positive. But it's on either end of the graph, not what's happening in the middle. So I think of horizontal asymptote is where is the graph plateauing, if it's plateauing. Right? So if it's going to plateau somewhere, where is it going to plateau? If I was making a profit and I went, oh, it's better 1 week, less than 1 week, and I kept going, oh, this is about where it's plateauing. So it's where it plateaus at the ends of the graph. So it's your end behavior. So if the degrees are the same, then you're looking at the coefficients, because these guys, like we looked at the numbers, these guys are always going to cancel out. If it was 2 million over 1,000,001, it's still 2 divided by 1, so it's 2. The plus 1 is just a little bit. That plus 1 is the part that makes it not touch the line, right? That's what makes it an asymptote. It's not quite exactly 2. It's a little off. That's the plus 1. But it's getting very close to 2. So we put in a bunch of numbers, right? So we put in 2 million. Then I asked to put in numbers here. So the more numbers we put in, the bigger numbers we put in. Remember, we're looking at the ends of the graph, the two end behaviors. If we put in 100, 1,000, a million, what I found is if you put in, say, 6 million minus 4 over 2, 1, 2, 3, 4, 5, 6, square it. When I put that in, it was getting very, very small. When I put that in, 1, 2, 3, 4, 5, 6, minus 4, get the top, divided by, and then I have 2 times 1 million, 1, 2, 3, 4, 5, 6, close that up. Oh, I didn't need to close that up. So squared. Close that up, and then I get this. And look, I got 1.4999 times 10 to the negative 6. That means you're moving the decimal place 6 to the left, which means this is 0.00000, 5 zeros, 149. Very, very small. This is why it's approaching 0. Because when you get bigger numbers, this exponent, even though it's only 1 bigger, is this number here on the bottom is going to get so much bigger than this one. Imagine if you had $1 million versus $1 million squared dollars. That's way bigger, right? So this is getting bigger faster than the top is getting bigger, so that's why it plateaus to be 0. So whenever the degree on the bottom is bigger, then it's going to plateau to be 0. Okay, so here, the next one. So that's higher degree in the denominator. So that was this one. So again, I look at the degree and I go, okay, degree on the top is 1. How do I know? Because the biggest one is 1, right? The degree on the bottom was 2. If the degree on the bottom is higher than the degree on the top, I know it's approaching 0. Does that make sense? Okay, so the next one. If I look at this one and I say the degree on the top is 4, the degree on the bottom is 2. Does that make sense? Look at the highest degree of each polynomial. Then you go, okay, so this is the scenario where the higher degree is in the numerator by more than 1. Right, so then we're looking at this scenario. So the numerator is 4. The denominator has a degree of 2. So that means that this is getting bigger faster than the denominator can catch up. So then for here, we're going to say has no horizontal asymptote. So I'll cross that off and say no horizontal asymptote. Okay, so no horizontal asymptote at all because the degree of the top is getting bigger faster than the bottom, so it's not going to plateau to anything. Okay? All right. So these are the scenarios. Now, one last scenario is what if I look at this and I say the degree on the top is 2, the degree on the bottom is 1, right? Is that okay? I'm getting the degrees, highest power, highest power. This degree here is by exactly 1 higher, right? So it's higher by exactly 1. Exactly 1. So if it's higher by exactly 1, okay, exactly 1, that means that this is going to become an oblique asymptote. Oblique asymptote. Only if it is higher by a degree of 1. The reason why is because when I divide it in, what happens when I divide it? Can I do this one synthetic, or do I have to do polynomial? How do I know if I can do synthetic? Yep, linear on the bottom. So let's do synthetic. You could do polynomial. It's up to you. I'm going to do synthetic here on the side. So I'm going to do synthetic. So -1. And then 1. In the middle, you have to put 0. Does that make sense? Remember this? 0 for the placeholder. 4. Okay, and then we're going to do this. We're going to say, okay, I'm going to drag this down. It's 1. -1 times 1 is -1. Add it. It's -1. Right? And then -1 times -1 is 1. Add it. It's 5. That's my remainder. If my remainder was 0, what would I say? Yeah. That's a factor. And if it's a factor, that means I could cross it off, which means it's a... If you can cross up whole, exactly, back to beginning. So we're hoping that it's not a 0. If it's a 0, that means, oh, shoot, we forgot to check if it was a whole first. I should have done that first and go back to the beginning of the question and say it's a whole. So I got to go all the way back. So this one's not a whole, so I don't want the remainder to be 0. So not 0, right? If it's 0, then it is a whole. Okay, so if it's a 0, it's a whole, then I should restart that a little bit. So then from this, what do I have left, this polynomial? This becomes y equals, that's x minus 1. Does that make sense? X minus 1, so that I put over here, x minus 1. So that goes over here. Yes? The remainder, it's just that's the part that pulls it off the asymptote. We leave it alone, and we don't need it. So this is where the dashed line will be. So this is going to give me this nice little dashed line. Wait, there's my ruler here. So that means that this is going to be at -1. So it's at -1, positive slope. So I'm going to get something like this. So that is my y equals x minus 1. Right? Y equals x minus 1, and then the remainder is the part that's pulling it off of the asymptote. So that's where that's coming from. Does that make sense? So you want the remainder. We don't do anything with it. The equation is just there. Yes? From here. So when I divide an x into an x squared, what's my quotient going to be? So I'm writing the quotient. My quotient would be x, because it's an x squared divided by x, so that would be x minus 1. So if I had x cubed plus x squared minus 4x, right, so plus 3, divided by x minus 4, what would my quotient be? I know my quotient. When I divide that in, my answer here, x goes into that. My answer is x squared, right? So you know that's 1 less, because you're dividing a linear into that. So if I'm dividing a squared by an x, my answer for my quotient will be x minus 1. It's when you wrote your answer when you did synthetic, right? So whenever you did your synthetic, right? So if I did this synthetic and I put 4 here, my answer would be x squared, because I'm doing a 3 by an x. Do you remember? Does that make sense? Right? So when you did the synthetic, you divided by a linear, so your answer would be x squared, because you know it's an x into x. So if I said 3, 5, 6, it would be 3x squared, 5x, right? So that's how you wrote your quotient. So that's your synthetic. Okay? Yes?
I also had another question.
Yep.
If you have like a hole in the graph, that means there's a horizontal asymptote, right? So
No.
vertical.
No, a hole on the graph is something separate. So a hole on the graph means that, say, I have this and I have a hole in the graph. A horizontal asymptote is this, where it's approaching an asymptote. So a hole and an asymptote are not the same thing. So a hole is a hole when you cross it off, right? And an asymptote is a separate thing. Holes and asymptotes are separate, different things, yes.
So it's just like a hole in the function.
A hole in the function, yes. A hole is just a hole. So what you do is, just like what we taught in grade 11, so if I had this and I said x minus 3, I would cross it off, so, and that'd be 1. My graph is the horizontal line, y equals 1, whatever's left over, right? So if I have that off, then what's left over is y equals 1, but there's a hole at my graph at 3, right? So whatever's left over, yeah.
So if there was no remainder, like if you just divided, that would be the equation of the line, and then
Yeah,
the whole
that
is just
if
the whole
if
is
there's
the
no remainder, then you have to go back to the beginning of the question and go, oh shoot, that's actually a hole. I should cross it off and then find out the remainder, right?
Here, what would the line look like on this graph?
The line,
Because it's x minus 1 is the asymptote, but that's also the equation.
the line is x minus 1. This is the x minus,
But it's not, isn't it 5 remainder, it's not plus 5.
no, the x minus 1 is the dashed line. X-
Isn't x minus 1 with 5 remainder also the equation of the graph?
Because you're dividing, you're just simplifying the
Like
x
you're simplifying
squared
it.
plus 4 divided by x plus 1.
No, you're not crossing it off. So you're not crossing it off. So you're getting this part confused, right? So when you have a hole, you cross it off. So when I had this, so say if I had y equals, let me do a better one. So 2x, x minus 4. So if I cross that off, my hole is gone. I write what's left over, right? Like that. I graph what's left over. So this is what you're asking, right? This is my y equals 2x. And then I poke a hole at 4.
There's no remainder.
Okay, there's no remainder. This, I don't cross off the bottom from the top. You don't cross it off.
Then what does the graph look like?
We're going to talk about that in a bit. So the question is, what does the graph look like? We'll talk about that in a bit, but that's not it. So we don't get to cross off anything. This division that we did gives us the dashed line, but we're not crossing anything off because mathematically you can't cross it off. The division doesn't work. If it does become 0, that means it was a hole and you have to restart the question like this. If it's not 0, then it gives you the dashed line, and then we'll talk about how the rest of the graph works in a bit, yeah, because we're going to have to do the horizontal asymptote, everything else. But we don't get to cross it off, right? So we don't cross it off. This is still my function, and then we do this, and we're going to talk about the rest of it later on, okay? But yeah, so that's all we know right now is that there's an oblique asymptote, and that's all. Okay, so then that's all we know so far, and we will come back to what the rest of the graph looks like in a bit. That'll be in 5.3. Right, but right now we know the asymptote is there. Yes, question?
Can you just do the synthetic to find the oblique asymptote?
Yes, so the synthetic is only to find this dashed line. The 5 is to reassure us that it wasn't a hole, that it actually is an asymptote, and it's being pulled off the asymptote a little bit. Does that make sense? Is that good? Okay, so I want to go over the types one more time. I'll pause the recording.